then we approximate it by replacing these diagonal matrix. In this case, we can easily calculate the derivative, or the inverse of the matrix, and so on. Also, one last thing we need to know.
May I ask about the approximation of the baseline using the diagonal matrix?
Yes.
If all of the non-diagonal elements are zero, does it mean that our function has no cross dependencies between different?
In a way, yes. It means, okay, if we assume that, okay, if we have a quadratic problem, it means that for this matrix, it like diagonal dominant. Yes, and all of diagonal elements are close to this place. That's true. Okay. Yes, it is not the best thing to do, but actually it is the best thing we can do in applications. If you can come out with something smarter on approximating of Hessian matrix to make it invertible, I suppose we will give a Nobel Prize in economics. But okay, this is not an easy problem to solve. And we need another approximation because, okay, actually calculating the second derivatives is not easy and easy thing to do. To do so, we need another observation, now not from optimization, but from statistics. And another question to the audience. Do you know what is a Fisher information matrix?
Sure.
Who knows?
I heard about.
Okay, it's very good. Basically, we can say that our problem machine learnings are basically the problem of the estimation of some parameters by maximizing some function or minimizing some function. In machine learning, typically we are talking about the loss function and we want to minimize the loss function. Also, in statistics, typically we are talking about the likelihood function and maximization it. Often we can say that basically the likelihood is the minus of our loss function. So basically it is two equivalent optimization problems because in the first place we just minimize some error, in the second option you just maximize minus errors, basically equivalent problem statements. And actually, people from statistics were also interested in properties on specific estimation problems. If we have a specific problem, but to characterize how good it is. Basically, one example of how we should assess this is to understand how good is the behavior of this function in neighborhood of the 2 point. And basically, if we have better so-called better Hessian matrix, we converge actually faster in the neighborhood. And basically it means that we want to be more convex, more strongly convex here. And again, we are assessing how close the logarithm of the likelihood to a quadratic function. Because if it's close to the quadratic function, then we are happy and we will solve everything pretty fast. But this is not what we are interested too much right now. We are interested in another interesting fact about this thing. If we take the expected value of the second derivative of the likelihood function, this is actually equivalent to our Hessian, yes? Because basically in Hessian we take the second derivatives and also we actually take the expectation or some approximation of it because of a typical form of the loss function. Basically, if we're talking about the loss function, we can decompose it for our sample of size m of some loss function defined for some object. Yes, we can take, say that we inside it have the logarithm of the likelihood here for specific x, I, given w. So how good is our prediction? For example, for linear regression, closed function, our minus likelihood, has a convenient form of pretty close to this. So we just take the square difference between our prediction by a linear model xi plus post times w and the target function, the target value we want to predict value I. So it means that basically when we are taking mainly these objects from our true distribution, it would be an approximation of the expectation of this logarithm of f of x I. Yes? So basically, we are looking at this thing and we want to optimize it, hoping that this sum, the logarithm of fxi by I taken from the sample would be close to the expectation. This again is a talk about closeness of the true risk. This is our true risk, and depending on the parameters w, and our empirical risk that we denote f hat m. To say that it is empirical because it has hat, and also m denotes the sample size. So we hope that these two guys are close to each other, and again we have the same story about our approximation. So we have this approximation to hold, and we can take the similar approach when talking about the second derivatives. If you take the second derivative on the left side and take the second derivative on the right side here, we also would have a good approximation. Yes, at least we hope so. So basically we would have a good approximation. Also there is a theorem that says that under some regularity conditions, instead of calculating the second derivative, we can calculate the product of two first derivatives. So basically this guy, d2, is close, when you take the expectation, to this guy, the product of the first derivatives. I don't want to explain it. You can try to do it on your own and find the proof if you don't want to solve it on your own. But basically, we can say that this guy is close to the Hessian. This guy is exactly this guy. So we can approximate the Hessian in a diagonal form by just calculating the expected squared product of this derivative and this derivative. Okay, and given that we have diagonal methods, we can take these derivatives only as diagonal. So we now have the full pipeline. We need to define and to explain what is going on in anagram methods.